In this video, we're going to talk about the factorization of polynomials over a field. Now, by the term over a field, I mean that the polynomials have coefficients in the field, and it's very important in this section that we're working over a field, not a ring. So examples of fields are the rational numbers, the real numbers, the complex numbers. An example of something that's a ring but not a field is the ring of integers. Okay, so let f be a field, and if we have a polynomial in x with coefficients in f, and then if we have a number alpha in our field, f, we say that alpha is a 0, sometimes we'll also use the word root, of this polynomial p of x in f, this is referring to the alpha being in f, if p of alpha is equal to 0. So this is terminology that's familiar from high school algebra. To find the roots of a polynomial, you set it equal to 0 and solve for x. Okay, so for example, let's look at the polynomial p of x is x squared plus 1. Now, this is a polynomial in q adjoint x, r adjoint x, and c adjoint x, because its coefficients, which are 1 and 1, there's also some zeros in front of x, but you can ignore those. Those coefficients come from the rational numbers. They also are therefore in the real numbers and the complex numbers. So we can consider this polynomial as a polynomial in the ring of polynomials with coefficients in Q, coefficients in R, or coefficients in C. And it turns out it matters, at least for this question of roots in the field, which field you're looking over. So x squared plus 1 has no roots or zeros when you're restricting your attention to roots in the rational numbers or the real numbers. Because any real number, when you square it, that's going to be bigger than 0 or equal to 0. But then when you add 1, it's definitely going to be bigger than 0. So this has no solutions or zeros. In other words, if you have this equation x squared plus 1 equals 0, that would have no solutions in the rational numbers or the real numbers. But then if you allow complex numbers and then you set x squared plus 1 equal to 0 and solve for x, subtracting the 1 over, we get this, and x then taking square roots is the square root of plus or minus I. And so there's two zeros in C, plus or minus I, to this polynomial. So this example illustrates that the question of having roots or zeros matters what field you're working over or in. We use both prepositions to denote the same kind of idea. Okay, let's do another example. X squared minus 2, and once again, because the coefficients are integers, negative 2 and 1, this polynomial is in all three of these fields, and in some other fields as well. Okay, so much the same story. So in this case, it has, it has no zeros in Q. That's because if we try to set x squared minus 2 to equal 0, then solving that equation, we get x equals the square root of plus or minus 2, and square root of 2 is not a rational number, it's an irrational number. You can't express it as a fraction, and so therefore, this polynomial has no zeros or roots in Q or over Q. Okay, but then if we go to the real numbers, or the complex numbers, this polynomial does have roots because the roots are plus or minus square root of 2, and the square root of 2 is in the real numbers. It's also in the complex numbers. Now let's go to a field that's probably not something you encounter in high school algebra. Let's take the field Z3. As a set, it's 0, 1, and 2. And you might say, well, how is this an element of, how is this a polynomial with coefficients in Z3? Well, you can think of this negative 2 as being in Z3 in the sense of negative 2 is the same as 1 mod 3. And so any polynomial with integer coefficients can be thought of as being in these rings of modular arithmetic. Negative 2 is the same as 1. Okay, and then I claim that this polynomial has no zeros in Z3. Well, why not? Well, we can just try to guess or check that there's only 3 choices for what a possible 0 could be when you're working over Z3. 0, 1, or 2, and if you plug in x equals 0, you don't get a final answer of 0. If you plug in x equals 1, you get 1 squared minus 2, which is not 0 in mod 3 land, and if you plug in x equals 2, you get 2 squared minus 2, which is 2, which again is non-zero in mod 3 land. So this polynomial has no zeros in or over z3. But now let's work over z7. Again, you can choose any prime, and then z mod that prime will be a field. And so this question of roots of a polynomial over a field, yeah, you can answer. And yeah, once again, we consider x squared minus 2 as having coefficients in z7 by thinking of negative 2 as the same as 5 mod 7. Why is it 5 mod 7? Well, negative 2 plus 7 is 5. And so that's how you know, which one of these numbers is minus 2? It's 5. Okay. So then what are the zeros of x squared minus 2 in z7? Well, it turns out there's 2 of them. And again, this is just by going one by one and checking until you hit a 0 in mod 7. So I won't check verbally 0, 1, or 2, but that's what I did mentally anyway. And then let me go to 3. 3 squared is 9. Subtract 2 is 7. And in mod 7 land, 7 is the same as 0. And so we get a 0 of this polynomial, namely the number 3. So this is probably pretty surprising to you if you haven't seen this before. It's very different from high school algebra. We're saying that over this field z7, this polynomial has a root for now. That root is 3. And it also has another root, 4. 4 squared minus 2 is 16. And, 16 minus 2 anyway, and that's 14, which is 0 in mod 7 land. So this polynomial x squared minus 2 has 2 zeros, 3 and 4. And we'll see that in general, a polynomial of degree n can have at most n zeros when you're working over a field. Here's something you've also seen before in high school algebra, but maybe a little differently. So let f be a field. And well, we're talking about the quotient remainder theorem for this ring, the polynomials over that field, the polynomials in X over that field. So suppose we're given 2 polynomials with coefficients in F, so that these coefficients an, bn, bm, and so on up to a0, b0, they're all numbers in the field F. So that field could be like the complex numbers, the rational numbers, the real numbers, but it can't be the integers because the integers aren't a field. I mean, these numbers can be all integers. Yes, that's allowed. But what I'm going to say after that is I might have to allow non-integer coefficients. Okay, so what we're going to try to do is basically take f of x and divide by g of x. And just as when you take one integer and divide by another, you get a quotient and a remainder, the same thing works for polynomials. And so we can, polynomials over a field, that's very important. And again, by over a field, I mean the coefficients of the polynomials are in a field. A field, again, is where you can divide by non-zero elements. Okay, so when we divide our polynomial f of x by g of x, we're going to get a quotient, q of x, and polynomial q of x with coefficients in the field, and then another polynomial, the remainder, r of x, with also coefficients in the field. And if f of x and g of x start with integer coefficients, these polynomials, quotient and remainder, might not have integer coefficients. They'll at least be rational. They'll have rational coefficients. But anyway, okay. One other important point is the remainder. The degree of the remainder is less than the degree of the polynomial you're dividing by. And this statement here is really just long division of polynomials. Because if you just try long division, take f of x and divide by g of x, you can slowly, step by step, cook up this quotient q of x, and then if this remainder, has degree bigger than or equal to m, you can divide one more time by g of x and get a smaller degree remainder. Long division was very tedious in high school algebra, and so I'm not going to really ask you to actually do it by hand. We can mostly work with it from a theoretical basis. And here's what I mean by using the quotient remainder theorem in a theoretical fashion. So we can use it to prove what's called the factor theorem. And this says that an element A in the field F is a 0 or a root of our polynomial f of x. in our ring f adjoint x, if and only if x minus a is a factor of f of x in this polynomial ring. What does this mean? Well, let's go to the proof and we'll explain what it means. So this is an if and only if statement, so there's two directions to prove. The first direction, or again, you can choose whichever direction to start with first, generally. So I decided to choose, suppose x minus a is a factor of f of x in this polynomial ring of polynomials in x with coefficients in f. So what that means is we can factor an x minus a out of f of x. In other words, f of x is x minus a times another polynomial g of x for some polynomial g of x in our ring. Okay, and then we basically substitute in x equals a into this equation. The formal way or fancy way of saying that, which is what our book does, but with good reason, but mathematicians typically don't say it this way. But we apply the evaluation homomorphism phi sub a. Again, that's just a fancy way of substituting in x equals a. Now, the left-hand side becomes phi of a of f of x. The right-hand side becomes phi of a of this whole thing. But because phi of a is a ring homomorphism, we can split up phi of this whole thing into phi of the first term, x minus a, times phi of the second term, g of x. Now, phi of a of f of x, by definition, that's just f of a. That's what this phi of a does, is wherever there's an x, substitute in a. Very simple. Now, similarly here, when we substitute in a for x, we get a minus a, and that's a 0. Substituting in a for x here just gets g of a. We don't know what the value of g of a is, but it doesn't matter because 0 times anything is 0 in any ring. And so we get that f of a is equal to 0, and that's what it means to say a is a 0 or a root of f of x. And that's what we were trying to show, that if x minus a is a factor of f of x, then a is a 0. This is actually quite something familiar from high school algebra. You just probably were working with an actual field of numbers, like the rational numbers, rather than an arbitrary field f, but the point is that theorem still holds when working over a field. Okay, now conversely, suppose we have a number in the field f, call it a, that is a 0 of our polynomial. That means f of a is equal to 0. Now by the quotient remainder theorem, when we divide by f of x by x minus a, we get some quotient q of x and some remainder r of x, where the degree of r of x, the remainder, is less than the degree of x minus a, but the degree of x minus a is 1, and so the degree of r of x is 0, which means r of x is a constant. In other words, it's a number. It has no x, no dependency on x. So we get that f of x is some quotient times x minus a plus a remainder. And now let's plug in x equals a. And so f of x turns into f of a minus a becomes 0. R has no dependency on x, so it just stays r. And our assumption is that f of a is 0. And so we get that r is equal to 0. And so that means that f of x is q of x times x minus a. This r part is 0. And so we can factor f of x as x minus a times q of x. And that's what we wanted to show. As a corollary, let's prove the following theorem. So it says that over a field, and this is going to be important that we're working over a field, a degree n polynomial f of x with coefficients in this field f can have at most n zeros in the field f. Okay, so here's a proof. It's, suppose we had a 0 a sub 1 in our field. That's a 0 of f of x. Then, by the theorem we just proved, we can write f of x as x minus a1 times some polynomial q of x, and the degree of q1 of x, and the degree of q1 of x is n minus 1, because when you multiply a degree 1 polynomial by a degree n minus 1 polynomial, you'll get a degree n polynomial. That's one consequence of working in a field. It's also true if you're working over an integral domain. Okay, so now if A2 is a different 0, so besides not equal to A1, then f of A2 is, well, let's plug in A2 in for x. So f of A2, we're assuming is 0. That's what it means for A2 to be a 0 of f of x. And then A2 minus A1, that's just this, and it's non-zero since we are assuming A2 minus A1 is not equal to 0, is non-zero. And then for x becomes A2. Okay, and so what we get is that Q1 of A2 times this number here is 0. Because we're working in a field, we can divide out by this number A2 minus A1, and what we get is Q1 of A2 is equal to 0. If we weren't working over a field, we couldn't go necessarily from this line to this line, especially if we were not working over an integral domain. Because something that's not an integral domain can have zero divisors, where two things are non-zero that multiply to 0. And so in that case, we could not conclude that this is 0. But because we're working over a field where you can divide by non-zero elements, we can divide by this non-zero element and conclude that Q1 of A2 is equal to 0. Okay, so Q1 of x is x minus A2 times some other polynomial Q2 of x, because that's the theorem we just proved, that if you have a 0, you can factor out an x minus A2. That's a familiar technique from high school algebra. Okay, and so on. So we keep factoring f of x as, well, initially we started with x minus a1 times q1 of x, but then down here we can factor further q1 of x as x minus a2 times q2 of x. So I've taken this equation and substituted in for q1 of x, and anyway, just after a bunch of times you get this type of factorization, and you can just keep going until you reach a place, a polynomial qr of x, that has no further zeros in f. Now you might say, well, how do you know that you can't go on forever? Well, suppose you go on up to a certain point r. By comparing the degree of both sides, you can conclude that r has to be less than n, because the left-hand side is a degree n polynomial. And then when you multiply by linear these polynomials x minus a1, x minus a2, and so forth, this is going to be a degree r polynomial, and so the degree on the right-hand side is at least bigger than or equal to r, and that has to equal n. So n has to be bigger than or equal to r. And so that's what we were trying to show, is that the number of zeros, which is r, is less than or equal to n, which is n is the degree of the polynomial. An instance of this corollary that you're familiar with is with the quadratic formula and polynomials of degree 2. If you're working with degree 2 polynomial, this is saying it has at most 2 zeros or roots over any field. And so you've seen that sometimes it has a degree 2 polynomial has 0 roots over the rational numbers. And over the complex numbers, the quadratic formula tells you that quadratic polynomial will have 2 roots, or 1 root repeated with multiplicity 2. Here's an example that illustrates the importance of working over a field. So Z4 is not a field. Again, Z4 is the numbers 0, 1, 2, and 3. And it's not a field because 2 is not an invertible element in it. 2 times 2 is 0. Okay, and consider this polynomial 2x. Then it has 2 roots, namely 0 and 2, because 2 times 0 is 0, 2 times this 2 is 4, which is 0 in mod 4 land. And so it has 2 roots, but it's of degree 1. The coefficient of the exponent on the x is 1. And so this contradicts the previous theorem, but that's only because we're not working over a field. Z4 is not a field.